Right, year 10. Today we're going to mark those questions we did last lesson, and then I'm going to give you a little extra one to have a go at it. Now, the important thing is that even if you did not do the silver or gold question from last lesson, I would like you to go through and make notes on this as we do it. So we'll start with the silver. A teacher used the equipment shown in the figure below to demonstrate the motor effect. Okay. Describe how Fleming's left-hand rule can be used to determine the direction in which the rod will move when the switch is closed, and state the direction. Well, first of all, you need to mention how you hold your hand. Luckily, it's given us it's the left hand, so we won't mention that. But you need to say that your thumb, okay, your first and second finger, or your index finger. So thumb first and second finger held at mutual right angles. Yeah, so the mutual I'd say is really important, but if you just said hold your fingers at right angles to each other, that means the same thing. Then you need to say that the thumb, okay, that equals the force. The first finger equals the magnetic field direction. Then the second finger, or your middle finger, equals the current. And that in itself is not enough. You need to add that. The force you point in direction of. Okay, this one, it points from north to south, and the current points in the direction of conventional current, okay, or you can say it points from the positive to the negative terminal. So it goes from positive to negative. Now, increasing the current can increase the force acting on the copper rod. Give one other way that the size of the force on this copper rod could be increased. So use a stronger magnet is the easiest one. You could increase the flux density. You could coil the rod. That one's kind of difficult because I haven't implied whether you can move this or not, but the easiest one to go for, which is increase the strength of the magnet. So get a stronger magnet. Right, nice and easy to start with. Now we'll get on to the question. So the copper rod in the figure above has a length of 7 centimeters and has a mass of that. When there is a current of that, the resultant force is 0. Calculate this and gravitational field strength of that. So let's do, well, we know we're using F equals Bill, right? So F B I L. They've given me gravitational field strength, so I'm going to put that in there too. Okay. Force. The resultant force equals 0. Right, calculate this. The current is 1.12. The length of the wire is 7 centimeters. So I should put the unit there, amps. Now, we should know from the previous lesson to convert this, it's 1 meter equals 100 centimeters, so you've got to divide this by 100. So this is 0.07 meters. Okay. Now, in the diagram, what we've got, what they're saying when they're talking about resultant force, you've got your horseshoe magnet here, and you've got your wire in the middle. Now, let's get the eraser on, because I kind of made a bit of a mess there. Right, let's try that again. Horseshoe magnet, you've got a wire. Now the mass of this object, or the weight I should say, sorry, the weight of this object, okay, is like this. Weight. The magnet, or the motor force, I should say, the motor effect is pushing that way. And what they've said, because the resultant force is 0, that means this is equal to that. Now, hopefully, we can remember from another topic that to calculate your weight, it equals the mass times strength of gravity, which we have. And if we can calculate the weight, because we know the resultant force is 0, the weight and the force must be equal. So the questions tried to mislead you here by saying the resultant force is 0, but they're talking about something different. And I know that's a bit mean because we haven't talked about resultant forces yet. So we can work out what F equals. Well, first of all, let's write it properly. We'll say we're working out the weight. So weight equals 4 times 10 to the minus 4 kilograms times by 9.8. And I'm just going to get my calculator. 4 times 10 to the minus 4 times by 9.8 equals... So my weight equals 3.92 times 10 to the minus 3. So 3.92 times 10 to the minus 3, and that's 8 newtons. So what I'm going to do is 1, 2, 3, if I want to put it in non-standard form, decimal place to the left 3 times. Now I've got enough to work out what B equals. So let's write out my equation. F equals B-I-L. Now from yesterday I showed you that B equals F divided by I times L. But we'll do it without substituting, we'll do it without rearranging, sorry. We'll substitute the numbers in. So 3.92 times 10 to the minus 3 equals B times 1.12 times 0.07. In case you're unsure where I got those from, this was my force that I calculated. B is just B. This was my current, okay, and this was the length of the wire in meters. Now let's put that. First of all, we've got like a slightly easier thing to do here. You know how to rearrange simple equations. So first of all, let's simplify this. What's 1.12 times by 0.07, and that is this number. So I've got B times by 0.0784 equals 3.92 times 10 to the minus 3. Now, if I just want B by itself, I had to get rid of this. If I had something different happening, say I had 50 equals X times by 10, what would you do to get rid of that 10? Well, you divide this side by 10 and you divide this by 10, so that would cross off and that would be 5 equals X, which you know how to do. Just because the numbers are more complicated, you're doing exactly the same thing. So I'm going to divide this side by 0.0784, so that cancels, and then I'm going to divide this side by 0.0784. So 3.92 times 10 to the minus 3 divided by 0.0784 equals So B equals 0.05 Teslas. Now, these kind of questions become difficult because we're using numbers like this, okay? We're using numbers like this, right? You need to get yourself a scientific calculator or get very used to using the one that's integrated into the computer. So there's the silver one. Let's do the gold one. And I'm going to skip. Actually, no, I'll talk about this first one. Now, it says here, when a current is passed through a wire from A to B, the reading on the balance increased. Suggest why? Well, you've got to use Fleming's left-hand rule for this. Okay. If you use Fleming's left-hand rule, you will find, so let me get it right, so north to south, the current's going from A to B. So using I'm going to try and draw what my hand says here. I've got my finger, my first finger is pointing that way. Okay. My middle finger is pointing this way, so then my thumb is pointing up. Okay, my thumb is up. This is my thumb, this is my first, and this is my second finger, right? Remember, the thumb is the force, so I know that this wire feels a force going upwards. Now, this wire is feeling the force going upwards, but this magnet is the one that's pushing it upwards, right? So this magnet feels a force in the opposite direction. So, when a current is passed through a wire from A to B, the reading on the balance increased. Explain why. Well, one, if you pass a current through a wire, okay, it creates a magnetic field around the wire. So, magnetic field around wire. 2, got to use Fleming's left-hand rule to show that the magnetic field from the wire, they interact with the magnetic field from the permanent magnet. I'm shorthanding this just because you can pause it, and I want to get on to the other question. So, using Fleming's left-hand rule, the wire will move upwards. Well, so the wire feels a force going upwards, so the magnet, the permanent magnet, feels an opposite force, an equal and opposite force going down. Now, so that is why that happens. The student increased the current in the wire. Sketch a graph showing the relationship between current and magnetic force on the wire. Now, you have got an equation, F equals BIL. It says, let's only look at this and this. So you can ignore these two. Sorry, we were looking at magnetic. Show relation to current and magnetic force. Yes, so you only look at them two. So you can ignore this and you can ignore this. So F equals to something. We're going to call it a constant I. Or if you're just ignoring everything, it's F isn't quite equal to, it is proportional to I in some way. Yeah, because, and if you've got one thing is proportional to another, you have got a straight line. Oh, like that. Can't really draw a straight line. Now, I would go that this is current. Okay, and then this is force. Because generally, you change the current, which affects the force. You can't change the force on the wire to affect anything else. The force is something that happens. The thing that you can affect is the current flowing through that wire. Anyway, next question. Kind of a bit similar to what we've seen before. Right. F, B, I, L. Right, the length of the wire in figure 1 that is inside the magnetic field equals this. 4.8 times 10 to the minus 2 meters. I'll put in the units in now, so I'm checking that they're correct. The current in the wire is 0.80 amps. The reading on the balance, they've given me a mass here. So that's a mass equals 1.2 times 10 to the minus 3 kilograms. They've given me the gravitational field strength, 9.8 newtons per kilogram. Calculate this. So I'm sorry if I went through that too quickly. This is why you do this every single time, because now I can see I've got F equals Bill. I've got two extra things that do not, two extra variables that do not appear in this equation, but I need to figure out what that is to calculate B. So the question has told me to calculate B, so I can kind of ignore it. But I need to fill in this blank here. So again, we know from the last question at least, weight equals mass times gravity. Okay, so the weight equals 4.8 times 10 to the minus 2 times by, sorry, that is not the mass. I apologize. I have written the wrong thing down. Let's get rid of that. Go away. So let's try that again. The mass is this one here. So the mass is 1.2 times 10 to the minus 3. Gravity on the Earth is always 9.8 newtons per kilogram, and you have to remember that. So let's get my calculator out and type that in. 1.2 times 10 to the minus 3 times that by 9.8 equals, and you get the weight is 0.01176 newtons. Good. Now we're ready to do F equals Bill. And because we've done it a few times now, I'm not going to sub in and rearrange. I'm just going to write the equation already rearranged. F equals B times L. Sorry, again, why am I writing the wrong thing? B equals F divided by I times L. My brain has decided to stop working. Let's substitute those values in. Well, we know F equals 0.01176 divided by, we know I is 0.8, and we know L is 4.8 times 10 to the minus 2. So let's extend that. Now you need to resolve what happens on the bottom of the equation first, or if you've got a scientific calculator, you just press the button on your scientific calculator that just looks like this, and you write the fractions in as they appear, and it magically calculates it for you. 0.1176 over 0.8 times by 4.8 times 10 to the minus 2 equals, and we get 0.30625. We'll do it to 3 significant figures, just because it's easiest. So my answer B equals 0.30625 Teslas, and over here I'm going to write B equals 0.306, and that's 3 significant figures T, and we're done. Now I have put a question in the folder. Let me just find that a second. Here's the folder. There it is. Here's the question. If it loads. Where are you? There it is. This question here. This is the hard bit. You've got to work out the moments. The mark schemes are there, so if you get stuck, you can get pointers. Have a go at that. It's 8 marks. It should take you 8 minutes. It will probably take you longer because of calculations. Now, I have talked for long enough, so have a nice day and email me the work when you're done.